a lubricant, either oil or grease, should always be present in the bearings in small quantities. If not, the life of the bearing will be compromised by damage to the bearing surfaces. This damage can be avoided with proper cleaning and relubrication. The intervals for cleaning and relubing the bearings are in general long periods. It is easy to see when a bearing needs oil. For this, check the oil level indicator on your pump. However, it is different with grease. It is impossible to determine when a bearing needs more grease. This is because the grease in the bearing does not suddenly lose its lubricating properties. These properties are lost gradually over time. Production history and previous operating experience are a good guide to determine when to add more grease. The intervals depend on the grease properties, the size and design of the bearing, the operating speed, the temperature, and humidity. As a rule of thumb, in important process pumps, the grease in a bearing should be changed every 12 to 18 months. This will assure a reliable pump operation and service because time alone causes certain deterioration in the lubricating ability of grease. The intervals for cleaning and relubricating bearings should be more frequent if water or moisture is able to enter into the bearing chamber. Bearing can become contaminated from rain, pumps located under dripping equipment, morning dew, fog, and condensation. Entrance point could be through inadequate, worn or failed shaft seals, the breather cap, and the lube oil fill port. Be sure the new grease or oil is not contaminated. Grease is normally injected through a port or by removing the bearing end cover or housing cap. When injecting grease mechanically or hydraulically, remember to open the drain or expel port. The new grease will expel the old grease under pressure. Also, remember to close the drain port afterward. The amount of grease to be added is a function of the housing size and design and the size of the bearing. The grease should completely impregnate the bearing and fill the housing about 25% full. And remember, too much grease will lead to overheating. Now, to remove old grease from the bearing internals and the housing, first remove as much as possible by hand. Then flush the bearing and housing with warm kerosene, following by a flush with mineral oil. If the old grease is caked and hardened, then you can use the following method. First, soak the bearing and housing in heated kerosene. Then slowly rotate the bearing by hand. Then rinse the bearing with clean kerosene or degreasing solvent. And again, rotate the bearing's outer race by hand while applying a modest axial and radial load to the balls and races. Finally, soak and rinse again as necessary until the bearing rotates freely and smoothly. Once all the old grease is removed from the housing and the bearing is cleaned, it should be thoroughly inspected for damage. If the bearing is not damaged, it can be repacked with new grease of the correct type and consistency and reinstalled in the equipment or stored for future use. To store the bearing, wrap it completely in wax or oil paper, then place it into a storage box, as seen here. Now, the following table contains some simple do's and don'ts for handling and working with bearings. Memorizing and practicing these suggestions will extend the surface life of rolling elements bearings. This table is also available as a downloadable PDF file attached at the end of this section. Now, another important factor when using bearings is to have an accurate monitoring and measurement of the bearing working temperature. We often have a tendency to place a hand onto a bearing housing to measure the bearing's operating temperature. If it feels cool, we're confident that all is well inside the bearing chamber. If the housing is hot to the touch, we get worried about a potential failure, and we spend time and effort to lower the temperature, hoping to gain a clear idea of what's actually happening inside the housing. The fact is that the human hand is not a good thermometer, and it can give false temperature signals. In studies of human touch defining hot, hot varies somewhere between 120 degrees and 130 degrees Fahrenheit, depending on the individual. The human hand is worthless above this arbitrary point to estimate the temperature. Rolling element bearings lubricated with grease can operate safely in the 200 degrees Fahrenheit range. In fact, the upper temperature limit of the grease is the real operating limit of the bearing. It is not the bearing metallurgy. The temperature at which the grease carbonizes is the bearing's operating limit. Bearings are perfectly safe at 160 degrees Fahrenheit. This is actually good for a bearing because of the expected lubricant flow at this temperature. It is obvious that all bearings will operate at some temperature above the surrounding environment without additional cooling. The resulting temperature is composed of three factors. First, frictional heat is generated inside the bearings from contact between the rolling and stationary elements. Second, conductive heat is added to frictional heat. This is heat from the shaft bringing the temperature of the pumped liquid and also the radiated heat of the surrounding equipment in the area. Third, the amount of heat to be dissipated away from the pump's bearing is a function of the conductivity of the lubricant, the surface area of the bearing housing, and the temperature and motion of the surrounding air. These three factors work to bring about a stable operating temperature. This temperature should be less than the upper limit of the oil or grease. You need to investigate any unexplained rise in the bearing temperature. This could indicate imminent failure. You can add one more shot of grease, but if the temperature doesn't reduce immediately, don't continue adding any more grease. First, rule out obvious reasons for the increase. It could be that the temperature in the surrounding area has changed. So ask yourself the following questions. Has the weather changed? Has new heating generating equipment been installed in the vicinity? Or has there been a change in the temperature of the pumped liquid? If the answer to these questions didn't give you a good explanation to the rise in the bearing temperature, then what you can do next is to check the assembly for unnecessary thrust and radial loading, coupling misalignment, or over-tightened pump packing. Then remember again that the temperature can go up from improper lubrication practices. Excessive grease causes the bearing to sling and pack the grease against the internal housing wall. The grease will then become an insulator, and the bearing will run dry if the grease cannot return to the sump. Excessive oil causes foaming and air bubble entrainment as the rollers and balls crush into the fluid. Air is a good insulator, and the air doesn't lubricate or dissipate heat. Insufficient oil or grease leads to increased friction from metal to metal contact, and inadequate oil and grease are also sources of excessive frictional heat. Finally, some pumps that handle hot fluids have bearing chambers designed with thermal jackets and heat exchangers installed at the factory. These devices have connections for isolated water flow through or around the bearing housing. You should not use high-temperature grease with artificially cooled bearings. The grease won't flow properly, and the result will be consistent with inadequate lubrication. Sometimes, at pump startup, the bearings may seem to run hot. This may be heat actually generated by the bearing seals and not the bearings. After the seals seat and settle, the temperature should go back to normal. And this brings us to the next video about bearing seals. Among the newer developments for industrial pumps is the bearing mechanical seal. Two types of bearing mechanical seals will be discussed in this video, and these are the labyrinth seal and the lip seal. There are actually two basic concepts to designing these seals. One concept incorporates rotary and stationary faces held together with spring tension like standard process pump seals. The other basic concept utilizes magnets to hold the faces together. The flexibly mounted faces permit a small degree of axial and radial movement of the shaft without compromising the sealing ability. These seals perform well to completely separate the environment inside the bearing chamber from the environment outside the bearing chamber. These seals have proven effective in retaining grease and oil, and especially the oil fogs, inside the bearings. By holding positive pressure, neither contaminants nor humidity can enter into the bearing chamber. Let's start by examining the labyrinth seal. As a bearing shaft seal mounted into modern industrial pumps, the labyrinth seal is composed of a rotary unit that spins with the shaft and a stationary unit mounted into the bore of the bearing housing around the shaft. Labyrinth seals are considered non-contact seals. The rotary and stationary units do not actually touch each other. However, they are in very close proximity. Its operating principle utilizes centrifugal grooves with openings to an external gravity drainage. The dual purpose of the labyrinth seal is to prevent external contaminants like dust and water from entering into the bearing housing, while it maintains the lubricating grease or oil inside the bearing. The principle is quite simple. If a dust particle or drop of water tries to enter into the bearings through the seal, it is caught into the labyrinth of centrifugal spirals and ushered toward the external drainage. And if the bearing lubricant tries to exit the housing through the seal, it is trapped into its own labyrinth and returned back toward the oil sump. Now, before I show you a 3D animation of a labyrinth seal, let's take a look at the following figure. So here you can see the rotating shaft. Here you have the bearing housing, and now you recognize the rolling elements, which in our case here are balls, the inner ring or race, the outer ring or race, and remember the good practice for the oil level, which should be halfway up the lowest rolling element. And what you can see here is actually the labyrinth seal. And recall that it is made of a rotary unit that spins with the shaft and a stationary unit mounted into the bore of the bearing housing around the shaft. And to enhance the sealing action, the labyrinth seal utilizes O-rings and ring gaskets, as depicted here. Now take a look at the following 3D animation showing a labyrinth seal for bearings from Garlock. This non-contacting seal consists of a stator and a rotor assembled to form a labyrinth with no wearing part. The stator and rotor are precisely spaced by the unitizing ring to create that type labyrinth while keeping the critical tolerances, avoiding metal-to-metal contact between the stator and the rotor to reduce friction and metal shaving that could enter the bearing chamber. Now any contaminant attempting to enter the bearing chamber will be captured in the outboard drain groove and expelled through the drain port in the stator. Meanwhile, on the bearing side, bearing lubricant is captured by the inboard drain groove and directed back into the housing. Let's now shift our attention to the lip seal. The lip seal or oil seal used on modern centrifugal pumps is actually borrowed from the automotive industry. The lip seal was born with the invention of the car transmission and the universal joint in the early days of the family car. It really hasn't changed much in design since the 1920s. Now take a look at the following 3D animation. Here you can see the rotating shaft, and on the left side you can see the bearing with the outer ring, the balls, and the inner ring. And what you can see here is the lip seal. The outside diameter of the lip seal, as you can see here, fits and sits into the housing bore, and the inside diameter with the elastomeric lip rides onto the spinning shaft. And as you can see from this animation, the lip seal keeps oil and grease in the bearing housing and prevent ingress of dust and dirt from the outside. This lip seal will work well within its designed life, which is about 2000 hours. And at about 2000 hours, one of two things can happen to cause failure to this lip seal. Either the frictional heat from the spinning shaft burns and cooks the rubber lip, or the rubber lip eats a groove into the shaft. But how can a soft elastomeric rubber lip cut a groove into a stainless steel shaft? In fact, one of the components of stainless steel is chromium. A layer of chromium oxide is visible on the surface of stainless steels. That is why stainless steel appears to be chromed. As the stainless steel shaft spins under the rubber lip, the chromium oxide particles embed into the rubber lip. After a few revolutions, the rubber lip of the oil seal becomes an abrasive lip, which eats a groove into the stainless steel pump shaft. The rubbing action abrades the pump shaft, removing metal and depleting the chromium content of the stainless steel, which further accelerates its erosion. When the rubber lip can no longer maintain contact within the spinning shaft, the oil or grease can leak out of the bearing housing. Contaminants can enter into and destroy the bearings. When the lip seal is changed with the bearing change, the new lip rides into the old groove cut by the previous lip. And that is how a $6 rubber lip seal can take out a $300 bearing and $1,000 stainless steel pump shaft, about 4 times per year.